But I'm not sharing, am I? Oh, God. Sorry. We'll restart again. Okay, that's right. Share clip with audio. Start again. Simplest version is something.
Yeah, so if the sigma matrix is like shifting, is like cycling through all the entries of the vector, why doesn't the last entry become just like 1?
First, you formulate the problem on infinite lattice. No boundary conditions. It just, every integer has a lattice size from minus infinity to plus infinity. And then you write this Kronecker delta, which says if I was at the lattice side k, after I apply this Kronecker delta or the shift operator, one above the diagonal, everybody marches one step to the left. So what used to be 1 is now 2, etc. Then you say, I can't put this on computer, it's an infinite lattice. So let me just take a block of n sides that I can put on a computer that becomes a finite matrix. So then you just write it as above the diagonal. And what you notice is that, there are zeros on diagonal, and then above diagonal, there are ones. And first thing you say, well, let me put everything else to 0. Now, that operator is a nasty operator. We use it in quantum mechanics all the time as raising, lowering operator, but it has a property, it's nilpotent, which means that when you multiply a vector by that operator, what used to be in site 1 at the first place is now, a field 2 is in the first place because shift has shifted all the fields. And you go down to f phi of n minus 1, that's the last field. But then what that matrix does, it substitutes 0, not 1, 0. So then when you apply 2, you move everybody else, and what's happening is they're marching over the precipice, and you're just losing the first n values of your vector. If you do this n times, you just annihilated the original vector and you get a 0. So that's a thing that you do, which, in literature is called Dirichlet boundary condition or something. It's some boundary condition that in continuum you'll understand as well. So you realize it's not enough to say I have a shift, but I have to explain boundary conditions whenever I make it finite. If you make sure that when the last element of the vector has been shifted one space up, you take the guy that was thrown away at the top and put it as a new entry at the end, then you'll be cyclically shifting through the vector. And that's why you put in the matrix 1 in the lower left corner.
Okay, but then why is that the same as multiplying the vector by omega to the k? Because shouldn't the 1 be in the last?
First, 2 steps. First step is just matrix algebra. And we notice that if we are cycling the components of the vector, eventually what used to be the last component becomes the first. Mm-hmm. That happens after n minus 1 steps. And the next step, what used to be first component is again a first component.
Right.
So there is always finite cycle on it. And that means that applying the matrix shift operator, this matrix with off-diagonal elements, n times is the same as applying identity. Now that means that this equation satisfies a characteristic equation, because as a matrix, it satisfies equation that matrix to the power n minus 1 equals 0. Now I have this Hamilton-Cayley theorem that says characteristic equation for the matrix is the same as characteristic equation for number x. So I get a polynomial, and polynomial is very simple. It says x to the nth power minus 1 equals 0. Now, one obvious solution is x equals 1. But we know that the fundamental theorem of algebra says we have to have n roots. So the rest must be either in a complex plane. So, if dimension is even, then you'll find also that -1 is a solution. If the dimension n is odd, you'll find only that one a real solution. But then you realize in a complex plane, I can be on a unit circle in a complex plane. And I also have a solution which says that I take nth root of unity in a complex plane, which means, the first little that we call omega. And then because of symmetry or problem, omega squared, etc., they just run in same increments in a complex plane on a unit line. So that's how you get to omegas. So sigma in this notation is a matrix. It's a thing that acts on 1,000-dimensional space, for example. And omega is a number. It's just the root of the unity. Now, once we have eigenvalues, then we have a procedure of converting eigenvalues into eigenspaces of the big matrix by using projection operators.
Oh, okay, I see. So the omega to the k is actually just if you raise that to the nth power, that's just 1. So
yeah, that's just property of a complex number with unit, unit magnitude and complex phase. If its phase is rational in units of 2 pi over n, that means that as you raise it on powers, you just move around the unit circle. And if you do it n times, you come back to unity.
So I guess my question was sort of like I know that if I do this n times, I get the same vector back. So I see that it's just 1 times the same vector.
Yeah.
But then if
So
you do it 1 time, apparently the eigenvector is the same eigenvector, but the eigenvalue is now omega to the k.
Yeah. So what happens is, we have this procedure of obtaining eigenvectors when we have eigenvalues. So step number 1 in this analysis is almost always you try to find the eigenvalues first. That's at least conceptually easy because you're solving an ordinary polynomial equation in variable x, so just or z in a complex plane. So that's step number 1. So then you get eigenvalues. Now, then there is a procedure that says every eigenvalue has an eigenspace or eigenvector, but actually eigenspace, usually it's more dimension than 1 in the, associated with it. So how do you do that? You go back to your big matrix and you look at Hamilton-Cayley equation, which is a product of the matrix minus eigenvalue time unity n times. You erase one of the factors in that. Now the product is not 0 anymore because you removed one of the factors. And then you divide it by, omega k minus omega j and to normalize it correctly. And that's a projection operator. So what I'm giving you is, I'm saying, the stuff I taught you originally, you actually use all the time. But the way you are taught Fourier transforms, you don't see it because what you're taught always, and I'll do it next week, is that you look at an integral over dx from minus to plus infinity, e to the I p dot x, if it's in more dimensions, or px if it's 1 dimension. And for some reason that works. And then you do the algebra and, it works. So my whole purpose this week was to tell you, this is consequence of symmetry. You only use, and when do you do this? You only use Fourier transforms when you have translational symmetries. And if you do this as matrices, it's totally obvious. You just, you do it as 2 by 2 matrix, 3 by 3 matrix, and you understand it forever. And then you take limit of, n large, very large number of steps on a circle. That's called continuum, computerese. And in that limit, you realize that you can write, e to the wave number times nth lattice position. You can rescale it in a perimeter of the circle, and you define something called momentum rather than wave number, which has that included in it, and you get your 2 pi's and stuff like that. But that's just the limit of this procedure.
So when you say when you say the derivatives are non-local, isn't that just a consequence of the fact that even for an ordinary derivative, like first order, you cannot technically measure it with just 1 point. You need 2 points. The curvature, you need 3 points, right, to get it.
Yeah, I personally find it, you can say this, but I get very confused in continuum limit, because in continuum limit, everybody is evaluated at a point. So when when Newton or Leibniz define a derivative, f of x is another function that's defined at this point. So I personally don't see that derivative as an operation. To me, just looks there is a sequence of functions. There is original function, its first derivative, second. I can plot them all, and they all look equally good. And there is a rule for them. So that's why I went through the whole trouble of teaching you matrices, linear algebra, or reviewing it, to make it very clear that derivative is an operator. It's not, and you're correct. In the limit, it's still an operator, but for me, it's impenetrable. But in matrix notation, it's totally obvious. In matrix notation, what happens is you have a derivative, and you have antiderivative, which is called integral. Now, in matrix representation, integral is a sum over the sides. And what this operation of local comparison and its opposite, the integrations, tell you is that when I look at, antiderivative, when I'm integrating over something that's differentiated, etc., I'll get influence all over the space. And in usual courses, you'll be taught Green's functions in linear algebra that do this. They tell you that, the field that you experience at the point is a consequence of the charges every place, or charge density in all space. So that operation, which is 1 over Laplacian plus blah, 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 which is called Green's function, that operation is global. And in this discretization, you see this by finding out that if you take sufficiently many inverses, I did it as a power series of Laplacian. If you take sufficiently many inverses of your original differential, you will actually fill the whole space. So, all makes sense. It's just that the other one makes me very queasy, because it's so easy to make errors when you're in a continuum. And people have made amazing errors that lasted forever in theoretical physics by forgetting that this is actually a limit, and that there are Jacobians around, and there are all these things. So that's why I'm doing this. And I'm doing this because I'm trying to differentiate between mathematics, which is beautiful, and what we actually do. Now, all our calculations today are done on finite grids. Yeah, there is no research calculation that's not done on finite grid. All the courses are taught like this is still 19th century, but that's not our reality in this millennium. So I'm trying to teach you a modern course.